In today's video, we're going to look at electrophilic aromatic substitution. Remember that aromatic rings, in this case we're looking at benzene, are exceptionally stable. And so when they react with an electrophile, here I've just used a generic Y+, it's got to be a very strong electrophile to react with the stable aromatic ring. And so in the first step of an EAS reaction, or electrophilic aromatic substitution, one of the pi bonds in the aromatic ring is donated to the electrophile. And that generates a carbocation and adds the electrophile to one of the carbons involved in that bond. This carbocation is resonance stabilized. We can move that positive charge around. So we move it once there. To get that carbocation. And we can move it again there. To get this carbocation. In a second step, some base is going to come in and deprotonate the hydrogen on the same carbon that the electrophile added to. So this pair of electrons is going to come in and remove that hydrogen and kick those electrons down, which regenerates the aromaticity in the ring. And you have substituted a hydrogen with the electrophile. Unlike alkenes, aromatic rings do not do addition reactions. That is, this carbocation is not susceptible to nucleophiles. And that's because this proton here is super acidic, because when I deprotonate it, I regenerate aromaticity. And so the driving force to regenerate aromaticity is so great that this carbocation is never going to react towards a nucleophile. Let's take a moment to look at the reaction coordinate diagram of this reaction. So I'm going to draw a reaction coordinate. Over here we have enthalpy, or energy, and along the bottom, reaction progress. And we start at an arbitrary level of benzene here. This is a two-step reaction, and so I expect to have two transition states, so two humps with an intermediate in between. And this very first step is the rate determining step. And its activation energy is quite high because I'm breaking aromaticity when I add the electrophile, this generic electrophile, to that aromatic ring. So I'm breaking aromaticity. And then we're reforming aromaticity, and so that next step is a little bit lower. And the product and reactant are not very far apart because they're both aromatic. And so, again, the rate determining step is this first step, and that is equivalent to this transition state. This intermediate here is the resonance stabilized carbocation that we generated before. The second step happens much faster than the first step because the second step has the driving force of regenerating aromaticity rather than breaking it. There are 5 big classes of electrophilic aromatic substitution that I want to talk about in this video, and they are halogenation, nitration, sulfonation, Friedel-Crafts, acylation, and Friedel-Crafts alkylation. All of these reactions are going to follow the same generic mechanism that we just saw here. In the first EAS reaction, we're going to replace a hydrogen atom with a halogen. So Br, Cl, or iodine. And we've seen Br2 or Cl2 react as electrophiles. But remember that when we're doing electrophilic aromatic substitution, we need a very strong electrophile. And so Br2 alone is not enough. We're going to treat this with Fibr or iron tribromide as well. And so the first thing that happens is we're going to generate a stronger electrophile than Br2. And so in a reaction where we have Br2 and iron tribromide is going to behave as a Lewis acid and accept electrons from one of the bromines on Br2 to generate this complex. Here. And now this terminal Br is very electrophilic, and it's going to accept some electrons from the pi system here, and these electrons are going to kick off there. And generate this carbocation, which again is resonance stabilized. It's got 3 resonance structures that look like this. And it's also going to generate FeBr4 minus. Then a base is going to come in and pull off the proton attached to the carbon that the electrophile or Br was added to. And so one of these Brs is going to come in and pluck that off and put those electrons there to regenerate aromaticity and form HBr and regenerate iron tribromide. Much like bromination of benzene, chlorination of benzene uses Cl2 and fecal or FeCl3. And again, the first thing that we have to do is generate a very strong electrophile. Cl2 is not strong enough. And so if we redraw these, This chlorine is going to give some electrons to iron. And you're going to generate this complex here, which makes this terminal chlorine very electrophilic. And it can accept some electrons from benzene and then kick its electrons back. And that's going to generate the carbocation. Not iron. Chlorine. The iron has a negative charge. And this carbocation is resonance stabilized. Let's draw its resonance structures. Here. And then this hydrogen is acidic and is going to be plucked off using one of these CLs that's going to generate chlorobenzene plus HCl and regenerate our iron trichloride. So the mechanism for chlorination and bromination are exactly the same. If you want to add an iodine to benzene, we typically do it a little bit differently, and I don't want to go into great detail about how this mechanism works. But essentially, this mixture of I2, sulfuric acid, and hydrogen peroxide takes I2 and generates 2 iodine cations. And an iodine cation is a much stronger electrophile than I2, and so it's going to react in the same way any other electrophile reacts with benzene. It's going to generate an intermediate that's resonance stabilized carbocation and then eliminate again to form iodobenzene. In the nitration of benzene, we're going to substitute a hydrogen for an NO2 group here, or a nitro group. And just like the halogenation of benzene, the first step is to generate a strong electrophile. And to do that, we are going to treat nitric acid with sulfuric acid and generate a nitronium ion. And that mechanism looks like this. Nitric acid has this Lewis structure, and it's going to react with H2SO4, which has this Lewis structure. And so to generate this electrophile, nitric acid is actually going to act as a base and pick up a proton from sulfuric acid to generate this intermediate. which will eliminate water by kicking these electrons up to nitrogen and that water off, which generates the nitronium ion, which is a positively charged NO2 in water. And this nitronium ion is a great electrophile that's going to react with benzene. And so this pair of electrons is going to come down and attack that positively charged nitrogen and generate this structure. And so notice that a nitro group, which we have now put on benzene right here, exists as a Zwitter ion with the nitrogen always positively charged, and one of the oxygens has a negative charge. I'm going to complete this Lewis structure with a carbocation. This carbocation is resonance stabilized. I'm going to abbreviate my nitro group. It's just NO2 now. And then a base, in this case it's probably water, is going to come in and pick up this proton, which kicks down to generate nitrobenzene. As the final product. In the sulfonation of benzene, we are going to replace a hydrogen with an SO3H group, like so. And just like all the other electrophilic aromatic substitution reactions, the first thing that we need to do is generate a strong electrophile. To do this, it's going to look very similar to the generation of the nitronium ion. One sulfuric acid is going to react with another molecule of sulfuric acid. And pick up a proton. This is going to generate a protonated OH, which can then be eliminated by water just leaving, and that is going to form the strong electrophile SO3H plus. This strong electrophile reacts with benzene just like all the rest to generate a carbocation intermediate that looks like this. Like the rest, this has 3 resonance structures that I am not going to draw. I'm just going to say that there are some resonance structures here. And at this stage, this proton is going to be deprotonated, probably using the water we just generated in the previous step. And this is going to generate this substituted benzene here. In Friedel-Crafts acylation, we are going to replace a hydrogen with an acyl group, which is a ketone with some carbon chain that I'm going to abbreviate as R here. In this case, R is this methyl group here. In Friedel-Crafts acylation involves an acid chloride, which is a functional group that we have not seen yet. So this is an acid chloride. You may also see this called an acyl chloride. This is, of the functional group is a carbon-oxygen double bond with a Cl attached to the same carbon. And in this reaction, the first step, you guessed it, generate a strong electrophile. Aluminum trichloride is a Lewis acid and is going to help us to generate a strong electrophile. This Cl is going to donate electrons to the aluminum and is going to form this complex here. A minus charge and a plus charge. The lone pair on oxygen can kick down and kick this chloride off, which is going to generate this oxonium intermediate and aluminum tetrachloride, which has a minus charge. This oxonium intermediate is a super strong electrophile. And so we're going to take some electrons and attack that carbon, which is going to kick up these electrons here and generate a carbocation intermediate. Here, like the others, this is resonance stabilized, but I am going to forego drawing those resonance structures and show this Cl. I'm going to draw it out a little more completely here. And this Cl is going to pick up this proton here. To generate this compound plus HCl plus aluminum trichloride. And you'll notice that in this reaction we have a second step that involves water. This is because the electrons on this carbonyl that we just generated can complex to aluminum here and form this intermediate. Like that. And this is where the reaction stops before you add water to it. Once you add water to this, I'm not going to show the complete mechanism of this, but if you remember from general chemistry, aluminum hydroxide is insoluble. And so when this complex reacts with 3 equivalents of water, I generate 3 HCl's and aluminum hydroxide, and my desired substituted benzene. And this is the final product of this two-step reaction. In Friedel-Crafts alkylation, I'm going to replace an H with an alkyl group that I'm going to abbreviate as R here. I'm starting to sound like a broken record, but just like all the others, the first step is to generate a strong electrophile. Aluminum trichloride can be used in Friedel-Crafts alkylation as well, and it's going to pick up some electrons from that chloride, which is going to generate this intermediate. And this chlorine that now has a positive charge is an exceptional leaving group. And so it's just going to leave to form this secondary carbocation plus aluminum tetrachloride. Carbocations are great electrophiles, and so this carbocation is going to react with benzene like so to generate a new carbocation that looks like this. Again, this carbocation is resonance stabilized, but I'm not going to draw out all of those resonance structures. This then reacts with the aluminum tetrachloride to pull off this H, or this proton, and regenerate aromaticity, which is going to form isopropyl benzene as the final product in Friedel-Crafts alkylation. So to sum up this video, electrophilic aromatic substitution is the reaction or the substitution of a proton on an aromatic ring with a new functional group. The way you do this reaction is you first form a very strong electrophile, and that electrophile reacts with benzene or the aromatic ring, and then a base is going to come in and eliminate the proton attached to the same carbon that you put your new functional group on. And that's going to regenerate aromaticity and produce your substituted benzene as the final product.